Hydrogen fuel cells created quite a stir for a while. Remember, the electric battery charges with electricity through an electrolyte. A fuel cell is very similar. However, it charges with chemicals. Rather than charge it with electricity, you put in hydrogen. It has a proton exchange membrane. The hydrogen would be in a much lower energy state if it combined with oxygen and became water. Neither hydrogen nor electrons can pass through this proton exchange membrane. However, this catalyst can separate the electron from the proton in the hydrogen, and the proton alone can migrate across the membrane. And so the electrons can accumulate here, and this becomes a positive charge. And so what you have is an electrical source. You can also drive this with an electrical source and drive this chemical equation backwards to create hydrogen. So if we had some clean source of electricity, let's say wind power, we could drive a fuel cell backwards to create hydrogen. This could be used to store energy to drive electric cars that used a fuel cell to generate the electricity. This received a lot of attention under the Bush administration. This technology, however, has a number of significant hurdles that have to be overcome before it can be usable. For instance, the efficiency of creating hydrogen or converting hydrogen to electricity is pretty low, on the order of 50%. It turns out it's much less expensive to take natural gas and strip the hydrogen from the natural gas itself in a process called natural gas reformation. Additionally, the catalyst requires platinum, which is very expensive. It can also be clogged by any impurities in the hydrogen, so the hydrogen has to be absolutely pure, which is very expensive. Additionally, you can't put a tracer gas in it like you can with natural gas. Natural gas has a smell because we put a tracer gas of thiols, which have sulfur in it. Sulfur would clog the platinum and destroy your fuel cell. Additionally, how are we going to transport this hydrogen? And crucially, how can we store it? Where we remember the graph before that hydrogen requires a huge amount of volume. It turns out that the high pressure tanks necessary to store enough hydrogen to give you any reasonable range in a car are going to have as much size and mass as an equivalent battery pack for an electric car. So all of these hurdles actually made this the perfect policy for the George Bush administration. I call it TNBT, the next big thing. It's perfect, it's unknown, it's untested, and it's way off in the future. And what it does, it allows you to not have to address the issue and the opportunities you have right at hand with you. And for George Bush, this was efficiency. Why don't we raise the CAFE standard? The CAFE standard is the corporate average fuel economy. Why don't we increase the mileage of the cars that Detroit is building? And so by focusing attention on the next big thing, they didn't have to go in and do what was obvious and in front of them. I want you to look for this in your cocktail party conversations. For instance, we have one in California. How about the super train, the 200-some-mile-an-hour train that we're going to produce in the future? What about the trains we have now? How could our 100-mile-an-hour train system work if we decided to make it work? And in San Pablo, of course, we have microhydro. How does holding microhydro in their future give them the opportunity to not address the challenges right in front of them? And that is improving their efficient use of electricity. Let's look at how we can improve the efficiency of the internal combustion engine by electric hybridization. So why does the internal combustion engine get such shitty efficiency? Let's take a look at the efficiency of an engine as a function of the power it puts out. And we'll compare a Brayton cycle and a diesel. So you see, is the internal combustion engine doesn't get really lousy efficiency. It can get up to 30% efficiency, but drops off drastically when you don't draw a lot of power, as opposed to the Brayton cycle, which can get up to 40% efficiency even at very low power output. So why is this the case? For lower power output with a gasoline engine or a diesel engine, you get decreased efficiency. So when you want to throttle down a diesel, you draw the same amount of air into the cylinder, but inject less fuel. The result is a decreased burning temperature of the gas. Decreased temperature means decreased Carnot efficiency. With a gasoline engine, you close the throttle so as the piston comes down, you draw in less air and gas mixture. In this process, the piston is pulling against a partial vacuum. You can think of it as a frictional loss as you drag the air through the tiny throttle. Both of these decrease efficiency. Additionally, both of these engines have internal friction, which results in the same amount of energy loss regardless of how hard you drive. But as you drive to lower and lower powers, that frictional loss or that parasitic loss constitutes a greater percentage of the engine's output. And so essentially, you get what you really want. And when we design and build internal combustion engines, we build them to kick ass. We build them so they can be as powerful as possible, and we don't really worry about what happens when we throttle down. Most cars have about 100 kilowatts of power potential that you can draw from, which is on the order of 100 horsepower. However, when we're driving down the freeway, we only need about 10 kilowatts or 8 horsepower to keep the car going. So we're only using about 10% of the engine's capacity, which might give us a 5 or 10% efficiency. So you get what you pay for. This would explain why efficient cars have small engines. Because then all the time, in order to just drive around, you have to drive the engine to a higher portion of its potential output. So the solution is you could just drive full throttle all the time and then turn your engine off. This is called surge and glide. So if we could floor our cars to get our cars going and then turn the engines off and coast to slow down, we'd get maximum efficiency. Well, there's a technology that lets us do that. It's a hybrid system. What if your car was driven by an electric motor, which you can turn off very easily, and it was backed up by a gasoline engine that could kick in and help it when it needed extra power, or could drive a generator to generate electricity to charge a battery for the electric motor? Then the gasoline engine would only kick on from time to time when the electric motor needed an extra push. And that gasoline engine would always be driven at full blast whenever it was turned on. Additionally, it could charge a battery to drive the electric motor. We like electric motors because they get really high efficiency, well over 90%. And because you'd only need the engine for backup, it would be undersized, and therefore whenever you use it full blast. You can use regenerative braking then. Regenerative braking is when you want to slow down rather than frictionally slowing down your wheels. You use the electric motor that drives the wheels as a generator, and you pull energy from the wheels, using it to charge the battery. With a plug-in hybrid electric vehicle, you don't even have to burn gasoline to run it. You can charge it at home from the grid. This allows you to use potentially combined cycle natural gas electricity at 65% efficiency, or better yet, maybe you have a wind farm that you're charging your car from. Let's look at two different kinds of hybrids, a series and a parallel. In a parallel hybrid, both the engine and the motor can drive the wheels independently. So the motor and the engine run in parallel. In a series, only the motor drives the drive shaft. The engine exists solely to push a generator to charge a battery for the motor. So in this one, the engine kicks on and runs full throttle when it needs to charge a battery. In a parallel, the engine kicks on when the motor needs more power to the wheels. Additionally, regenerative brakes can both be used to take energy from the wheel and use it to charge the battery. In this mechanism, the engine, through the regenerative braking mechanism, also can charge a battery. So I set out to experimentally determine the efficiencies or mileage of both electric cars and gasoline cars. I compared the Tesla Roadster and the Lotus Elise because they're essentially identical cars made on the same frame, but the Tesla is electric and the Lotus is gasoline. You can see they're both very sexy, very fast, high performance, very affordable, and have about the same weight and range. We measured the efficiency of the electric car in watt-hours per kilometer traveled, as opposed to miles per gallon of gas. So we can turn this around. Instead of miles per gallon of gas, we have kilometers per kilowatt hour of electricity used. So let's convert to kilometers per kilowatt hour. We can see the electrical efficiency is about 6 times greater than that of the internal combustion engine. However, in order for the electricity to get to us, we have to consider line losses. The efficiency of the grid is about 92%. And then the extraction of oil is about 80% efficient in that we have to use 20% of a gallon of gas of energy in order to get us a gallon of gas. However, maybe we had to generate our electricity from natural gas combined cycle at 50% efficiency. So the electric car uses electricity 6 times as efficiently as the internal combustion engine uses gasoline. However, if you look at it from terms of efficiency of use of primary energy, the electric motor would use natural gas to generate electricity about 3.5 times as efficient as the internal combustion engine uses petroleum from the ground. or only about 2.5 times as efficient if you generate your electricity with a single cycle coal. We know that the efficiency of the electric motor is about 90%, and the charge-discharge efficiency of a battery is about 86%, which yields a total efficiency of about 77% efficiency of turning electric energy from your socket into kinetic energy of the motor. And so when we divide that by 6, we get a driving efficiency of the internal combustion engine of the Lotus Elise of about 12.7%. So the electric car uses its electricity with about 77% efficiency, and the Lotus Elise uses its gasoline with about 12.7% efficiency. This knowledge sets us up for the last calculation I want to share with you. The question is, what if we use all renewable energy to drive? We could use solar thermal electric to drive our electric cars, or we could grow corn to make corn ethanol to drive our internal combustion engines. Both of these power technologies would use up valuable surface area of land in the sun, would use up water, and would produce carbon dioxide. So let's compare them. Solar thermal electric can convert sunlight to electricity with about 10% efficiency. So instead of 1,000 watts per square meter of sunlight power, you get about 100 watts per square meter of electricity. This converts to about 200 kilowatt hours per meter squared per year. In a cornfield, for a square meter of a field of corn, we can produce every year about 1/10 of a gallon of gas. We might have to use 0.08 of a gallon of gas to produce it in fertilizers and other energy expenditures, but we won't consider that right now. So taking this all into consideration, if we drive an internal combustion engine car with corn grain ethanol or switchgrass ethanol, or we could drive an electric car with solar thermal electric, and we can look at kilometer that we could be able to drive per square meter of land used every year. So corn grain ethanol would give us slightly more than 1 kilometer per square meter as opposed to slightly over 100 kilometers per square meter with electrical travel. So we could drive about 100 times as far using sunlight to fuel our car if we simply turn it to electricity and drive an electric car than if we try to grow corn ethanol and drive an internal combustion engine. In comparing the kilometers we could drive per liter of water used, we also find we could drive about 5 times as far, and the distance we could travel per kilogram of carbon dioxide emitted, because even solar thermal electric will emit carbon dioxide because you have to build the facility. We find that with solar electricity, we could drive about 10 times as far with the same carbon emissions as we could with corn grain ethanol, and a little over twice what we could drive with switchgrass ethanol. And so this is just a way to look at some of the environmental costs of the decisions we make and the technologies we use.